Somewhere in the darkness, there are objects so powerful, even light cannot escape them. That darkness isn't empty space. It's a black hole, where gravity becomes so extreme that light itself has no way out. This boundary is called the event horizon. It's a black hole, where gravity becomes so extreme that there is no known path back. And near the event horizon, something even stranger happens. To a distant observer, time itself appears to slow down. To someone watching from far away, the falling object would seem to slow, fade, and almost freeze at the edge. But from the falling astronaut's perspective, the story is very different. They would cross the horizon without seeing a solid wall or a sudden barrier. Once beyond the horizon, escape is no longer a matter of speed. Every possible path leads deeper toward the center. And deeper inside, gravity becomes uneven. The difference in force across an object can become so extreme that matter is stretched apart. Scientists call this effect spaghettification. Near a black hole, gravity can stretch matter into incredibly thin, elongated streams. And at the center lies the greatest mystery of all, the singularity, where our current laws of physics may no longer be enough to explain what happens. Black holes weren't first discovered by seeing them. Astronomers had to notice something invisible, affecting what they could see. Something invisible was pulling on the stars around it. And the more astronomers measured that motion, the harder it became to ignore. The object couldn't be seen directly, but its gravity gave it away. Whatever was hiding there had an enormous amount of mass packed into an incredibly small region. Decades earlier, Einstein's theory of relativity had predicted something extraordinary. Gravity wasn't simply a force. Massive objects could actually curve space and time. But proving a black hole existed required more than equations. Scientists needed to observe its shadow. So scientists connected radio telescopes across our planet, creating something extraordinary, a virtual telescope with the resolving power of an Earth-sized instrument.
Then, in 2019, humanity finally saw what had once seemed impossible, the shadow of a black hole.
The first black hole ever directly imaged was at the center of Messier 87, a galaxy roughly 55 million light-years from Earth. Is about 6.5 billion times more massive than our Sun. Its event horizon is so enormous, our entire solar system would look tiny beside it. And black holes aren't just distant monsters. At the center of our own Milky Way galaxy, one is hiding too. It's called Sagittarius A, and astronomers know it's there because nearby stars orbit something incredibly massive, packed into a tiny region. Some of these stars move at thousands of kilometers per second. Their incredible speed gives astronomers a way to measure the invisible giant controlling their orbits. Black holes don't just bend space, they bend time. The stronger the gravity, the slower time can pass relative to someone farther away. In extreme gravity, the difference could become enormous. A journey near a black hole could mean far more time has passed for the universe outside. And when black holes feed, they can become some of the brightest objects in the universe. Some launch jets of energy across millions of light years. And sometimes, black holes collide. When they merge, they send ripples through space-time itself, gravitational waves traveling across the universe. In 2015, scientists detected gravitational waves for the first time. For the first time, we weren't just observing the universe, we were detecting its vibrations. But black holes created an even deeper mystery. If something falls inside, what happens to the information that describes it? Does it disappear forever? Stephen Hawking proposed something even stranger. Black holes may slowly lose energy and eventually evaporate. Given enough time, even these cosmic giants could disappear. But there's a problem. Einstein's theory explains gravity on the largest scales, while quantum physics rules the smallest. Inside a black hole, both may matter at once. What we need is a theory that can describe both gravity and quantum physics at the same time. And right now, we don't have it. Some theoretical models raise an even stranger possibility. Could extreme space-time distortions connect distant regions of the universe? But there's no evidence that black holes are usable portals. These hypothetical shortcuts are called wormholes. Mathematics can describe them, but whether nature actually creates them is still unknown.
Black holes can also distort the universe like cosmic lenses, bending light so dramatically that distant objects can appear stretched, duplicated, or even hidden.
And sometimes, a star gets too close. The black hole's tidal forces can tear it apart, sending its material spiraling into space. We may never see a black hole directly in the way we see a star. Instead, we watch what happens around it, and let the universe reveal the evidence. Some black holes are millions or even billions more massive than the Sun, and the largest ones can influence the evolution of entire galaxies.
But one mystery remains. Where did the first black holes come from? Some may have formed from the dust in the extreme conditions of the early universe.
If some black holes formed this early, they could have had a head start, growing rapidly as the first galaxies in the universe began to take shape. And this creates another puzzle. Some black holes became enormous surprisingly early in cosmic history. How they grew so fast remains an open question. We know black holes exist. We can measure them, observe their effects, and even image their shadows. But what happens at their deepest point is still beyond our understanding. We can describe what happens around a black hole with extraordinary precision. But beyond the horizon, we don't yet know what reality truly looks like. Perhaps that's what makes black holes so fascinating. They remind us how much there is left to discover, even in a universe we've spent centuries trying to understand. And the search isn't over. New telescopes, new detectors, and new discoveries are giving us a clearer view of the darkest objects in the universe. And somewhere out there, another black hole may already be waiting to surprise us. The next discovery could change what we think we know about gravity itself. The universe may be filled with black holes silent, invisible, and drifting through the darkness, revealing themselves only when something gets close enough. For now, black holes remain one of the universe's greatest mysteries. We can see their effects, but the deepest secrets are still hidden beyond the horizon.
Black holes may be invisible, but their mystery is impossible to ignore. And perhaps the most fascinating question is not what we've discovered, but what we're still missing.
For more of histories and the secrets hidden beyond what we can see, subscribe to Codex Obscura and tell us, what mystery should we explore next?